Hello there. My name is Elara, and welcome to the Late Night Science Channel. Tonight, we're going to talk about something that, well, it might just change how you see the sky forever. You know, when you look up at night and you see those little points of light? Most people think that's it. That's all there is. But here's the thing. What you're seeing, it's almost nothing. Like literally less than a fraction of a percent of what's actually out there. And if you stick around, I'm going to tell you exactly what I mean by that. Oh, and if you enjoy these kinds of stories, the ones that help you drift off while learning something incredible, maybe hit that subscribe button. It really helps me keep making these for you. All right, so let's begin. So picture this. You're standing outside on the clearest night you've ever seen. No city lights, no moon, just you and the darkness. And you start counting stars. 1, 2, 3. You keep going. How many do you think you'd count? Take a guess. 1,000? 10,000? The answer is maybe 4,000. That's it. 4,000 stars, max, with your naked eye. And here's what's wild about that number. Those 4,000 stars, they're all in our galaxy, not scattered across the universe, just in the Milky Way. And they're all pretty close to us, cosmically speaking, within a few hundred light years, which sounds far, but it's nothing. It's like standing in your backyard and only seeing your immediate neighbors. Now, let me tell you about light years for a second, because this matters. A light year isn't a measure of time, even though it sounds like it. It's distance. It's how far light travels in 1 year. And light, well, it moves fast, really fast, about 186,000 miles every single second. In 1 year, that adds up to about 5.88 trillion miles. So when we say a star is 500 light years away, we mean its light has been traveling for 500 years just to reach your eyes. The light you're seeing tonight left that star before Galileo was born. Think about that for a moment. And those 4,000 stars you can see, they're the bright ones, the close ones. But the Milky Way, our galaxy, it contains somewhere between 150 and 250 billion stars. Most estimates put it around 200 billion. So for every star you can see with your eyes, there are about 50 million you can't. 50 million invisible stars for every visible one. Just let that sink in while you're lying there. The night sky isn't showing you the universe. It's barely showing you your cosmic neighborhood. Now, let's talk about what these stars actually are, because they're not all the same, not even close. Most stars, about 70 to 75% of them, are what we call red dwarfs. These are small stars, maybe 8 to 50% of our sun's mass, and they burn their fuel incredibly slowly. So slowly that not a single red dwarf that's ever formed has died yet. The universe isn't old enough. Every red dwarf ever born is still alive today, still shining, still burning hydrogen. And here's the thing, you can't see any of them with your naked eye, not one. The most common type of star in existence, and they're completely invisible to us without a telescope. Then you have stars like our sun, yellow dwarfs we call them. They make up about 7 or 8% of all stars. They live for around 10 billion years, give or take. Our sun is about 4.6 billion years old right now, so it's middle-aged, you could say. In another 5 billion years or so, it'll start running out of hydrogen in its core. When that happens, it'll swell up into a red giant, probably swallowing Mercury and Venus, maybe even Earth. Then it'll shed its outer layers and leave behind a white dwarf, a dense little ball of carbon and oxygen about the size of Earth, but containing half the sun's mass, and it'll just cool down over trillions of years until it's a cold, dark cinder. But then you have the massive stars, the giants and supergiants, stars that are 10, 20, 100 times more massive than the Sun. These stars, they're rare, maybe 1% of all stars, but they're spectacular. A single massive blue star can outshine 100,000 suns. They burn hot and bright and fast. The most massive stars only live a few million years. They consume their fuel so rapidly that they burn out almost as quickly as they ignite. And when they die, they don't just fade away, they explode. Supernovae, some of the most violent events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of normal stars. Now, you might be wondering, how do we know all this? How do we know how many stars are in the Milky Way when we can barely see any of them? Good question. The answer is, well, it's complicated. We can't count them directly. There's too much dust and gas blocking our view, especially when we try to look toward the galactic center. It's like trying to see through fog. So astronomers use tricks. They count stars in small regions where they have good visibility, then multiply by the total area. They measure the total mass of the galaxy using gravitational effects, then estimate what fraction of that mass is stars versus gas and dust and dark matter. They study other spiral galaxies similar to our own and use those as templates. And all these methods, they converge on that same range, 150 to 250 billion stars, probably around 200 billion. But here's where it gets really interesting. For most of human history, people didn't even know other galaxies existed. When astronomers in the 1700s and 1800s looked at fuzzy patches in the sky, they called them nebulae and assumed they were just gas clouds within the Milky Way. Some were gas clouds, sure, but others were something far more extraordinary. There's this galaxy, Andromeda. You can actually see it with your naked eye on a dark night if you know where to look. It appears as a faint, fuzzy smudge. For centuries, that's all it was, just another nebula. Then, in 1923, Edwin Hubble changed everything. He was using the Hooker telescope at Mount Wilson Observatory, this massive 100-inch telescope, and he found a type of star called a Cepheid variable in Andromeda. Now, Cepheid variables are special. They pulsate, getting brighter and dimmer in a regular pattern. And here's the key. The time it takes them to pulsate is directly related to how bright they actually are. So if you measure the pulsation period, you know the star's true brightness. Then you compare that to how bright it appears from Earth, and boom, you can calculate how far away it is. When Hubble did this calculation, he got a shocking result. Andromeda was about 900,000 light-years away in his initial estimate. We know now it's actually about 2.5 million light-years away. His measurement was off, but the key point was established. Andromeda couldn't possibly be inside the Milky Way. It was an entirely separate galaxy, containing hundreds of billions of its own stars, existing far beyond our own. The universe, in that moment, became incomparably larger than anyone had imagined. The Milky Way wasn't the universe, it was just one galaxy among, well, how many? That was the next question. Once astronomers knew what to look for, they started finding galaxies everywhere. Point a telescope at any seemingly empty patch of sky, and you'd find them. Dozens, hundreds, sometimes thousands of galaxies. The universe was filled with them. In the 1990s, astronomers did something audacious. They pointed the Hubble Space Telescope at a tiny patch of sky in the constellation Ursa Major. This patch appeared completely empty. You couldn't see anything there with your naked eye, or even with most telescopes. The patch was so small it could be covered by a grain of sand held at arm's length, and Hubble just stared at it for 10 days straight, collecting every single photon of light that reached it. The resulting image was called the Hubble Deep Field, and it was revolutionary. In that tiny, empty patch, Hubble found about 3,000 galaxies, 3,000 whole galaxies in a region you could cover with a pinhead held at arm's length. Most were incredibly distant, billions of light years away. Their light had been traveling for most of the age of the universe to reach us. Think about the math here. If there are 3,000 galaxies in such a tiny region, and you need about 12 million such regions to cover the entire sky, that suggests tens of billions of galaxies in the observable universe. Later observations went even deeper. The Hubble Ultra Deep Field found about 10,000 galaxies in an even smaller patch. And in 2016, a team analyzed all available data and arrived at a new estimate, about 2 trillion galaxies in the observable universe. 2 trillion, each one containing anywhere from a few billion to over a trillion stars. So let's do some math. 2 trillion galaxies times an average of, say, 100 billion stars per galaxy. That gives us 200 billion trillion stars. Written out, that's 200 000 000 000 000 000 stars. In scientific notation, it's 2 times 10 to the 23rd power. And that's just in the observable universe, the part we can actually see. There might be vastly more beyond our horizon. Now, I want to give you some perspective on this number, though. I'll warn you, it won't really work. The number is too large to grasp intuitively, but we can try. There are approximately 7.5 quintillion grains of sand on all of Earth's beaches. That's 7,500 000 000 000 grains. For every single grain of sand on every beach on Earth, there are about 27 stars in the observable universe. Some estimates say closer to 10 or 20 stars per grain, depending on which sand count you use, but the order of magnitude is correct. Roughly 10 to 100 stars for each grain of beach sand. So next time you're at the beach, pick up a handful. You're holding maybe a few thousand grains. For each one of those tiny specks, there are dozens of stars scattered across the cosmos. Each star a massive ball of nuclear fire, most likely surrounded by planets, potentially harboring life, existing in a galaxy somewhere in the observable universe. If every person currently alive started counting stars right now, 1 star per second without stopping, it would take humanity nearly 800 years to count them all. Generations would be born and die during the count. Entire civilizations could rise and fall, and we'd still be counting. And that's just the observable universe, the part we can actually see. The universe might extend far beyond that, possibly infinitely far. If the universe is infinite, then the number of stars is also infinite. There would be infinitely many galaxies, each containing billions or trillions of stars, stretching on forever in all directions. In an infinite universe, every possible configuration of matter would occur somewhere, and it would occur infinitely many times. There would be infinitely many galaxies identical to the Milky Way, infinitely many planets identical to Earth, infinitely many versions of you right now lying in bed listening to this exact story. This sounds like science fiction, I know, but it's a serious implication of an infinite universe with roughly uniform matter distribution. If space goes on forever and matter is spread out evenly on average, every possible arrangement must eventually repeat. We don't know if the universe is actually infinite. We can't see beyond the observable universe, so we can't measure whether space continues indefinitely. Current models are consistent with either a finite but extremely large universe or an infinite one. The data doesn't yet distinguish between these possibilities. What we can say with confidence is that the observable universe contains approximately 200 billion trillion stars. Everything beyond that is speculation, though educated speculation based on our best understanding of cosmology. Now, let's think about what these stars actually are, because understanding their nature makes their number even more impressive. A star is a sphere of plasma held together by its own gravity. At the core, if the star is massive enough and hot enough, nuclear fusion occurs. Our sun, for example, fuses hydrogen into helium in its core. Every second, about 600 million metric tons of hydrogen are converted to helium. In the process, about 4 million metric tons of mass are converted directly into energy, following Einstein's famous equation, E equals mc squared. That energy works its way from the core to the surface over thousands of years, bouncing between particles in the dense interior before finally radiating into space as light and heat. The photon that hits your face on a sunny day was created in the sun's core tens of thousands of years ago. It's been bouncing around inside the sun all that time before finally escaping. The sun has been doing this for 4.6 billion years and will continue for another 5 billion before exhausting its core hydrogen. At that point, it'll swell into a red giant, probably engulfing Mercury and Venus, possibly Earth, before shedding its outer layers and leaving behind a white dwarf that will cool over trillions of years. This is just one star, one ball of plasma converting mass to energy through nuclear fusion, and there are 200 billion trillion of them. The total power output is, well, it's almost incomprehensible. The sun produces about 380 trillion watts. If every star produced similar power, which is roughly correct on average, the total output would be about 7.6 times 10 to the 49th watts. That's 76,000 billion trillion watts flooding through space constantly. Not all stars are like the sun, though. They come in a spectacular range of sizes, temperatures, colors, and lifetimes. Red dwarf stars, as I mentioned, are the most common. They're small, with masses between 8 and 50% of the sun's mass. They burn their fuel incredibly slowly. A red dwarf can shine for trillions of years. The universe isn't old enough for any of them to have died yet. If 3/4 of 200 billion trillion stars are red dwarfs, that's about 150 billion trillion red dwarfs scattered across the cosmos, none visible to the naked eye from Earth, despite being the most numerous stellar type in existence. Yellow dwarf stars, like our sun, make up about 7 to 8% of all stars. They live for roughly 10 billion years before dying. That's still about 14 billion trillion sun-like stars in the observable universe. Then you have the massive stars, blue and white giants and supergiants, some over 100 times the sun's mass. These are rare, perhaps 1% of all stars, but spectacularly bright. A single massive blue star can outshine 100,000 suns. These stars live fast and die young, exploding as supernovae after only a few million years. The most massive stars live for only a few million years. They're so rare and short-lived that at any given moment, there might be only a few billion of them in the entire observable universe. That sounds like a lot until you remember it's a tiny fraction. Then you have stellar corpses, white dwarfs, the cooling remnants of stars like the sun, neutron stars, the crushed cores left by supernova explosions, black holes, collapsed stars where gravity has become so strong that not even light can escape. These aren't actively fusing elements anymore, but they're still there, still part of the census. When we count stars, we're counting all of these: newborn stars just forming from gas clouds, middle-aged stars steadily fusing hydrogen, dying giants, stellar remnants. The number includes the full diversity of stellar evolution, from birth to death. Now let's talk about planets, because stars rarely exist in isolation. Most have planetary systems. Until 1995, we knew of only one planetary system, ours. We suspected other stars had planets, but couldn't detect them. Then, in that year, astronomers found the first confirmed planet orbiting a sun-like star. It was a gas giant, about half Jupiter's mass, orbiting very close to its parent star. Since then, discoveries have exploded. The Kepler Space Telescope, operating from 2019 to 2018, found thousands of exoplanets by watching stars dim slightly when planets passed in front of them. As of now, in 2025, we've confirmed over 6,000 exoplanets, with thousands more candidates awaiting verification. The data reveals something remarkable. Planets are common, very common. Most stars have at least one planet. Many have multiple planets. Planetary systems appear to be the default outcome of star formation, not a rare exception. If most of 200 billion trillion stars have planets, the number of planets likely exceeds the number of stars. There might be 300 billion trillion planets, maybe more. The universe isn't just filled with stars, it's filled with worlds. We are particularly interested in rocky planets in habitable zones, the regions around stars where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it. Based on Kepler data, roughly 20 to 50% of sun-like stars have at least one rocky planet in the habitable zone. Let's be conservative and say 20%. 20% of 14 billion trillion sun-like stars is about 3 billion trillion potentially habitable planets. 3 million billion worlds where conditions might be right for life. That doesn't mean all these planets have life. Habitability requires more than just the right temperature. You need the right atmosphere, protection from radiation, geological activity to recycle nutrients, probably a magnetic field, and likely many other factors we don't fully understand. But even if only a tiny fraction develop life, the absolute numbers could be staggering. If 1 in a million habitable planets have life, that's still 3 quadrillion living worlds. If 1 in a billion develops intelligent life capable of building civilizations, that's still 3 trillion technological societies. These are wild speculations, of course. Our sample size for life is 1, Earth. We have no idea how common or rare the origin of life actually is. We don't know the odds of evolution producing intelligence. We don't know how long civilizations typically last before destroying themselves or dying out. But the sheer number of opportunities is what matters. With planets numbering in the hundreds of billions of trillions, even extremely low probabilities could produce vast amounts of life, simply through the law of large numbers. And yet, we've found no evidence of other life. No radio signals, no megastructures, no obvious signs of industrial civilizations. The universe appears silent. This is the Fermi paradox, named after physicist Enrico Fermi's famous question: where is everybody? If there are billions or trillions of potential habitats for life, and the universe has had 13.8 billion years for life to arise and evolve, we should see evidence of other civilizations. The fact that we don't is puzzling. Maybe life is extraordinarily rare and we're alone, or nearly alone. Maybe intelligence is the rare step. Maybe civilizations inevitably destroy themselves. Maybe they're hiding. maybe the distances between stars are simply too vast for contact to be practical. We don't know. What we do know is that the number of stars and planets provides ample opportunity for life to exist elsewhere, even if we haven't found it yet. Let's talk about how stars create the elements that make planets and life possible, because this connects us directly to those 200 billion trillion stars in a profound way. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur throughout space, not just in stars. This created hydrogen, helium, and tiny amounts of lithium. That's it, 3 elements total. Everything else, every other element on the periodic table, was created later, inside stars. Carbon, nitrogen, oxygen, the elements essential for life, were forged in stellar cores through nuclear fusion. Iron and nickel were created in the final stages of massive stars' lives. The heaviest elements, gold, platinum, uranium, were synthesized in supernova explosions and neutron star collisions. Stars are element factories. They take simple hydrogen and helium and fuse them into progressively heavier elements. When massive stars explode, they scatter these elements into space. That enriched material mixes with existing gas clouds and eventually forms new stars and planets. This cycle has been operating for over 13 billion years. Each generation of stars enriches the cosmos slightly more. The first stars contained almost pure hydrogen and helium. The Sun, which formed about 4.6 billion years ago, contains about 2% heavy elements by mass. That small percentage made Earth possible. Rocky planets require heavy elements. Life requires carbon, oxygen, nitrogen, phosphorus, and many others. Every atom in your body, except hydrogen, was created inside a star. The oxygen you breathe was forged in stellar cores billions of years ago. The calcium in your bones came from dying stars. The iron in your blood was synthesized in supernova explosions. You are quite literally made of processed stardust. This isn't poetic language, it's chemical fact. The atoms that compose you were created through nuclear fusion in stellar interiors, scattered into space when those stars died, incorporated into a gas cloud that eventually collapsed to form the Sun and planets, accreted onto Earth, and ultimately became part of living organisms. With 200 billion trillion stars operating as element factories over billions of years, the universe has produced staggering quantities of heavy elements. There's enough carbon for countless rocky worlds, enough oxygen for atmospheres and oceans on billions of planets, enough silicon and iron for planetary crusts and cores across the cosmos. The number of stars directly translates to the total chemical enrichment of the universe. More stars means more fusion, more element production, more raw material for complex chemistry, and potentially for life. Let me tell you about how stars are distributed across space, because they're not scattered randomly. They're organized into structures at multiple scales. Stars cluster into galaxies. Galaxies cluster into groups and clusters. Clusters organize into superclusters, and superclusters arrange themselves along filaments, separated by vast voids. Our Milky Way belongs to the local group, containing about 54 galaxies. Besides the Milky Way and Andromeda, the rest are mostly dwarf galaxies with 1 billion stars each. The local group is part of the Laniakea supercluster, which contains about 100,000 galaxies spread across 520 million light-years. Laniakea isn't bound by gravity, though. It's defined by galaxies' motions toward a common gravitational center called the Great Attractor. If you could map the entire observable universe, it would look like a cosmic web, filaments of galaxies forming interconnected strands with enormous voids between them. The structure resembles soap foam. Galaxies concentrate in thin sheets and filaments, like soap film, while the voids are like air inside bubbles, mostly empty. This structure arose from tiny density fluctuations in the very early universe. Slightly denser regions attracted more matter through gravity, becoming denser still, while less dense regions lost matter to their denser neighbors. Over billions of years, this created the web of filaments and voids we see today. The largest known structure is the Hercules Corona Borealis Great Wall, a filament of galaxies about 10 billion light-years long. It's so large, it challenges our understanding of cosmic structure formation. When you think about 200 billion trillion stars, remember they're not evenly distributed. Most exist along these filaments and in clusters at the filaments' intersections. The voids contain relatively few galaxies. If you picked a random point in space, you'd probably land in a void, far from any galaxy. The universe is mostly empty. Stars, for all their vast numbers, occupy only a tiny fraction of the total volume of space. Let's think about the future, because the number of stars won't stay constant. Stars are born and die constantly, and the balance between birth and death is shifting. Star formation peaked about 10 to 11 billion years ago, when the universe was roughly 3 billion years old. Galaxies were smaller, denser, and gas-rich. Stars formed at a furious pace. Since then, the rate has declined. Much of the available gas has been consumed or dispersed. What remains is less efficient at forming stars. Currently, the Milky Way forms about 3 to 5 new stars per year. That might seem small, but multiply across 2 trillion galaxies, and you get trillions of new stars being born annually across the observable universe. Eventually, star formation will slow further, and then cease. Galaxies will exhaust their gas reserves. The last stars will form, perhaps a trillion years from now, give or take. After that, no new stars will be born. Existing stars will continue shining for a while. Red dwarfs will last for trillions of years, but eventually they too will die. In about 100 trillion years, star formation will have ended, and most stars will have burned out. The universe will be much darker, populated mainly by white dwarfs, brown dwarfs, neutron stars, and black holes. In the far future, measured in timescales that make the current age of the universe look like an eye blink, the last stars will fade. The universe will go dark. But that's so distant, it's almost meaningless to contemplate. For now, and for billions of years to come, stars will continue lighting up the cosmos. The number we count today will remain roughly stable, shifting slightly as stars are born and die, but maintaining the same order of magnitude. Let's return to Earth and think about what all this means for us personally. You're standing on a planet orbiting one star among 200 billion trillion. Your sun is utterly typical, a yellow dwarf of average size and brightness. Your location is unremarkable, in the suburbs of a standard spiral galaxy in an ordinary part of the universe. From a cosmic perspective, you're insignificant. Your entire civilization has existed for perhaps 10,000 years, if we're generous. Modern industrial society is only about 250 years old. We've known about other galaxies for barely 100 years. In cosmic terms, we just got here. And yet, we've measured the universe. We've counted the stars. We've calculated distances to galaxies billions of light years away. We've understood our place in the cosmic structure. We're tiny and brief, but we're also capable of comprehending the immensity that contains us. That capability is extraordinary. We're matter that has become conscious of itself. Atoms arranged in such a way that they can ponder the nature of atoms.
products of the universe that can understand the universe that created them. When you look up at the night sky, you're seeing photons that traveled for years from distant stars, light that left Sirius 8.6 years ago, light from Betelgeuse that departed 550 years ago during the Renaissance, ancient photons completing journeys measured in centuries just to enter your eye and be absorbed by your retina, creating the sensation of seeing a star. You're connected across space and time to those distant suns. The atoms in your body were forged in stars that died before the sun existed. You're made of materials created inside some of those 200 billion trillion stars, recycled through multiple generations, eventually ending up on Earth and incorporated into living tissue. This perspective can be humbling. Your problems, whatever they are, occur on one small world among countless worlds. Your concerns are temporary and local. The universe doesn't notice your struggles. But this perspective can also be freeing. You don't carry cosmic significance on your shoulders. You're allowed to be small. You're allowed to have small joys and small sorrows. You don't need universal importance to matter. You matter to yourself and to those around you, and that's enough. Understanding the number of stars gives context. You're part of something vast and ancient, but you're also here now, experiencing this moment. That experience has value, regardless of cosmic scale. Now, let me tell you about something called binary stars, because most stars don't exist alone like our sun. The majority live in binary or multiple star systems, where two or more stars orbit each other, gravitationally bound for billions of years. In a binary system, two stars orbit their common center of mass, performing a gravitational dance that can last for the entire lifetime of both stars. These systems are incredibly common. Roughly half of all sun-like stars exist in binary or multiple star systems. For more massive stars, the fraction is even higher, perhaps 70 to 80%. Some binaries are wide, with the two stars separated by hundreds of astronomical units. These stars orbit each other over thousands of years and barely influence each other's evolution. Other binaries are close, with stars separated by only a few times their own diameters. These systems are fascinating because the stars can exchange material. If one star swells into a red giant, its outer atmosphere might spill over onto its companion. This mass transfer can dramatically affect both stars' evolution. Some close binaries are so tight that the stars actually touch, sharing a common envelope of gas. These contact binaries look like peanuts, two stars merged together, each maintaining its own core. Binary star systems produce some of the most spectacular events in astronomy. Type 1a supernovae, which we use as distance indicators, occur in binary systems where a white dwarf accumulates material from its companion until reaching critical mass and exploding. Nova outbursts happen when a white dwarf in a binary system accretes hydrogen from its companion. The hydrogen builds up on the white dwarf's surface until conditions are right for explosive fusion. The white dwarf briefly brightens by thousands of times, appearing as a new star in the sky, hence nova, meaning new. Then it fades back to normal, only to repeat the cycle years or decades later. Binary systems remind us that stellar populations are interactive. Stars don't just shine in isolation, they interact gravitationally and sometimes physically, exchanging material, influencing each other's evolution, creating phenomena we wouldn't see in single star systems. With 200 billion trillion stars and roughly half in binary or multiple systems, we're talking about 100 billion trillion binary systems, each one unique. Different mass ratios, different orbital periods, different ages, different stages of evolution. The diversity is staggering. Now, let me tell you about stellar nurseries, the places where those 200 billion trillion stars were born and where new stars are being created constantly. The Eagle Nebula, made famous by Hubble's Pillars of Creation image, is an active star-forming region about 7,000 light-years from Earth. Those towering pillars of gas and dust are several light-years tall. They're being eroded by intense ultraviolet radiation from nearby massive young stars, while simultaneously serving as birthplaces for new stars. Inside those pillars, dense clumps of gas are collapsing under their own gravity. Some have already formed protostars, infant stars not yet hot enough for nuclear fusion. These protostars are surrounded by swirling disks of gas and dust where planets will eventually form. The process is violent. Powerful jets of material shoot out from the protostar's poles, plowing into surrounding gas and creating glowing shock waves. These jets are driven by magnetic fields threading through the accretion disk. The Carina Nebula is another spectacular star factory containing some of the most massive stars known. Eta Carina, possibly the most massive binary star system in our region of the galaxy, contains a star over 100 times the Sun's mass. It's so massive and luminous that it's unstable. In the 1840s, it underwent a massive outburst, ejecting several Sun masses of material and briefly becoming one of the brightest stars in the sky, despite being 7,500 light-years away. Eta Carina will explode as a supernova sometime in the astronomically near future, perhaps within the next 100,000 years. When it does, it'll briefly outshine the full moon, despite its vast distance. The explosion will be visible during the day. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is the closest major star-forming region, at about 1,300 light-years distant. It contains about 700 stars in various stages of formation, from protostars still embedded in their natal gas clouds to young stars less than 1,000,000 years old.
This cycle plays out across the universe. Molecular clouds collapse, stars form. The most massive stars quickly ionize and disperse the remaining gas. A stellar cluster emerges. Over time, the cluster dissolves. The stars spread out. Eventually, some of those stars die, returning material to space, enriching future generations of clouds that will collapse to form new stars. Star formation rates have varied dramatically over cosmic time. The peak occurred about 10 to 11 billion years ago, when galaxies were smaller, denser, and gas-rich. Back then, the universe was forming stars at perhaps 10 times the current rate. Since that peak, star formation has declined. Much of the available gas has been consumed or dispersed. What remains is in more diffuse reservoirs that form stars less efficiently. The universe today produces perhaps 1/3 as many new stars per year as it did at the peak. This decline will continue. In 1 trillion years, most galaxies will have exhausted their gas reserves. Star formation will sputter out. The last stars will form. Then, no more. But that's so far in the future, it's almost meaningless. For now, and for billions of years to come, stellar nurseries across the cosmos continue producing new stars. The 200 trillion count includes stars of all ages, from newborns less than 1,000,000 years old to ancient stars formed when the universe was less than 1 billion years old. Now let me tell you about quasars, because they represent the most extreme stellar environments in the universe. A quasar is a galaxy with an extremely bright core, powered by a supermassive black hole accreting material. The black hole, typically a few million to a few billion times the Sun's mass, sits at the galaxy's center. Gas spiraling into the black hole forms an accretion disk, heated to millions of degrees.
This disk can outshine the entire galaxy's worth of stars, making the quasar visible across billions of light years. Quasars were common in the early universe, but are rare today. Most formed when galaxies were young and gas-rich, providing ample fuel for the central black hole. As galaxies aged and consumed their gas, quasar activity declined. Today's universe has few active quasars compared to the universe a few billion years ago. Most massive galaxies, including the Milky Way, contain supermassive black holes at their centers. Ours is about 4 million times the Sun's mass. It's currently quiescent, not actively accreting much material. But in the past, it probably went through an active phase when it was feeding vigorously and possibly shining as a quasar. With 2 trillion galaxies, and probably most containing supermassive black holes, we're talking about trillions of black holes. Most are dormant now, but when we look back in time by observing distant galaxies, we see more active quasars, revealing an epoch when supermassive black holes were growing rapidly and exerting enormous influence on galaxy evolution. Let me tell you about galaxy collisions and mergers, because galaxies don't exist in isolation. They interact, collide, and merge, dramatically reshaping stellar populations. When 2 galaxies collide, the stars themselves rarely hit each other. Space is mostly empty. The distances between stars are vast compared to stellar sizes. But the gas clouds do collide, and the collision compresses the gas, triggering intense bursts of star formation. The antennae galaxies, about 70 million light-years away, are a spectacular example. 2 spiral galaxies are in the process of merging. Long tidal tails of stars and gas stream away from the collision site, created by gravitational interactions. Within the collision zone, thousands of young star clusters are forming, each containing tens of thousands of newly born stars. In about 1 billion years, the 2 galaxies will complete their merger, forming a single large elliptical galaxy. The spiral structure will be destroyed. Most of the gas will be consumed in star formation or blown away by supernova winds. This process is common. Most large elliptical galaxies probably formed from smaller spirals. The Milky Way itself has absorbed several small dwarf galaxies over its lifetime. Evidence appears in stellar streams, rivers of stars from destroyed dwarf galaxies now orbiting through the Milky Way's halo. Andromeda and the Milky Way are approaching each other at about 70 miles per second. In about 4 billion years, they'll collide. The merger will trigger massive star formation as gas clouds collide. Eventually, after several close passes and perhaps 1 billion years of interaction, they'll merge into a single large elliptical galaxy. Our Sun will likely survive the collision. It'll be thrown into a different orbit, possibly ending up farther from the merged galaxy's center. Earth might survive too, though its orbit around the Sun could be perturbed. The solar system as a whole will probably emerge intact, orbiting in the new galaxy. During the approach, Andromeda will grow larger in the sky, eventually spanning several degrees across. When the galaxies interpenetrate, new massive stars will light up the sky. For observers on Earth, if Earth still exists and has observers, it will be spectacular. Galaxy interactions are fundamental to cosmic evolution. In the early universe, galaxies were smaller and closer together. Collisions and mergers were common. Large galaxies grew by cannibalizing smaller ones. This hierarchical assembly built the diverse galaxy population we see today. With 2 trillion galaxies in the observable universe, interactions and mergers are happening constantly, somewhere. Thousands of galaxy collisions are occurring across the observable universe at any given moment, each one reshaping stellar populations, triggering star formation, building larger galaxies through merger. Let me tell you about neutron stars, because these exotic objects represent one endpoint of stellar evolution. A neutron star forms when a massive star's core collapses during a supernova. The collapse crushes protons and electrons together, forming neutrons. The result is a sphere about 12 to 15 miles across, containing about 1.4 times the Sun's mass. The density is staggering. A teaspoon of neutron star material would weigh about 900 billion kilograms. The surface gravity is about 100 billion times Earth's gravity. Many neutron stars are pulsars, spinning rapidly and beaming radiation from their magnetic poles like cosmic lighthouses. As the star rotates, the beam sweeps past Earth and we detect a pulse. Some pulsars spin hundreds of times per second, rotating faster than a kitchen blender. The Crab pulsar spins 30 times per second. The fastest known pulsar spins over 700 times per second. The universe probably contains hundreds of millions of neutron stars, perhaps a few billion. Most are invisible, their emission too faint to detect. But those we can observe reveal exotic physics impossible to study on Earth. Matter at nuclear densities, magnetic fields strong enough to distort atomic structure, space-time curved by immense gravity. With 200 trillion stars in total, perhaps 0.1% have died as massive enough stars to leave neutron stars. That's still hundreds of billions of neutron stars across the observable universe, each one a monument to stellar death.
When we count stars, we're counting a population that spans the full life cycle, from formation through active fusion to eventual death and remnant stages. The complexity of this population, the diversity of stellar types and evolutionary stages, the range from the smallest red dwarf to the largest hypergiant, from newborn protostar to ancient white dwarf, all of it contributes to the richness of the census. 200 billion trillion stars isn't just a number, it's a population with structure, diversity, history, and ongoing evolution. It's the product of 13.8 billion years of cosmic chemistry and physics. It's the culmination of countless gas cloud collapses, fusion reactions, supernova explosions, and merger events. And remarkably, from one small planet, we've figured this out. We've measured it. We've understood it. We've placed ourselves within this vast stellar population and grasped our connection to it. Consider what goes into this estimate. Astronomers had to first understand that stars are distant suns. They had to invent telescopes capable of resolving distant objects. They had to develop photography and later digital cameras to capture faint light. They had to build spectrographs to analyze starlight and determine chemical compositions, temperatures, and velocities. They had to discover the relationships between stellar properties like mass, luminosity, and temperature. They had to work out stellar evolution theory to understand how stars change over time. They had to realize that fuzzy nebulae were actually distant galaxies containing billions of stars. They had to develop distance measurement techniques spanning from parallax for nearby stars to redshift for the most distant galaxies. They had to understand cosmic expansion, the Big Bang, and the evolution of structure in the universe. Each step required overcoming technical challenges, developing new technologies, and refining theories. The number we quote today, 200 billion trillion stars, represents the culmination of centuries of work. It's not a wild guess, it's a measurement-based estimate with quantified uncertainties that continues to be refined as better data becomes available. The search for answers continues.
The James Webb Space Telescope is revealing details invisible to previous instruments. Each new instrument will refine our senses, finding faint galaxies we've missed, detecting distant objects invisible before. But we're likely close to the true number. The order of magnitude is solid. Whether the final count ends up being 100 billion trillion or 300 billion trillion doesn't fundamentally change the picture. The universe contains stars in quantities vastly exceeding human scale, numbering in the hundreds of billions of trillions. What does this mean for us? The vast number of stars suggests numerous potential destinations, but also highlights the extraordinary difficulty of reaching them. Even the nearest stars are light years away, distances so vast that with current technology, journeys would take tens of thousands of years. We're likely confined to our local region of the galaxy for any foreseeable future. Perhaps humanity will eventually spread to nearby star systems, establishing colonies on planets orbiting other suns. But the vast majority of those 200 billion trillion stars will remain forever beyond our reach. This constraint shapes the search for life. If intelligent civilizations are scattered across the galaxy, each one is probably isolated by distances measured in tens or hundreds of light years. Communication would take decades or centuries for a single exchange. Physical contact would be nearly impossible. The universe might be filled with life, perhaps even intelligent technological civilizations, but the distances ensure we remain isolated from each other. This isolation makes Earth precious. It's not just our home, it might be the only inhabited world we'll ever physically access. If life exists elsewhere, and the numbers suggest it probably does, we're unlikely to find it nearby. The cosmic perspective also affects how we think about long-term human futures. On cosmic scales, human civilization is barely beginning. We've existed for perhaps 10,000 years in any organized form. The universe will continue for trillions of years. If humanity survives, if we navigate the challenges of the next few centuries and establish ourselves as a multi-planet or multi-star species, we could potentially exist for millions or billions of years. On those timescales, recorded history becomes a brief prologue. But we're not guaranteed to survive. Civilizations fail, species go extinct. Perhaps most technological civilizations don't last long, which might explain the Fermi paradox. The stakes are high because the potential is immense. If we succeed, humanity could witness the evolution of stars, the changes in galaxies, the long, slow future of the cosmos. We could become truly long-lived, persisting for timescales comparable to stellar lifetimes. Or we might fail. We might destroy ourselves through war, environmental collapse, or other catastrophes. The universe wouldn't notice. Stars would continue shining. Galaxies would continue evolving. The cosmos would proceed, indifferent to our absence. So, as you're lying there, drifting off, think about this. You're on a planet orbiting one star among 200 billion trillion stars. Each point of light you see represents a massive nuclear furnace, most likely with planets, potentially with life. The light entering your eyes has traveled for years or centuries to reach you. You're connected across space and time to those distant suns. You're made of atoms they created. You're part of the same cosmic story that includes all 200 billion trillion stars. This knowledge should inspire wonder. The universe is vast beyond human scale. It contains more stars than we could ever hope to visit. Yet we've counted them, we've measured their distances, we've understood their natures. We're small and brief in cosmic terms, but we're also extraordinary. We're conscious matter that can contemplate the cosmos, and that's remarkable. So, if you enjoyed this journey through the stars, maybe you'd like to explore more. There's another story waiting, just a click away, about mysteries even deeper than the ones we've talked about tonight. But for now, just rest. Let these thoughts drift through your mind like starlight through space. 200 billion trillion stars, each one a sun, each one part of the grand cosmic story. And you, somehow, wonderfully, are part of it too. Good night.